Now that we have formulated the universal compression problem, in this lecture we will see a very natural compression scheme which perhaps some of you have already used unknowingly, uh, and we will try to evaluate its performance. And the scheme is very simple. We will basically think of these symbols X as words, and we will take a look at a sequence. So think of a book, and this book is a sequence of words. And what we will do is we will essentially take all words, take the frequency of those words, and store that frequency vector. That's our compression scheme. And we would like to analyze this scheme. Let's start with the simplest version of this scheme, where the alphabet X is the binary alphabet. And we are looking at n-length binary sequences. So our scheme can be described as follows. This is a compression scheme. Okay. This relates to the schemes that we saw much earlier in the course, where we were thinking of two tables. So in this scheme, we make as many tables as the number of ones in the sequence, and we first store the number of ones, which tells us the identity of the table where we should look up for the sequence. And in that table, we have indexed all the sequences with these ones and stored them one by one. That's at a high level the scheme. So a scheme in the first step, what it does is, maybe I'll be a little bit more formal. Let me explicitly describe the scheme. So what's the input for our scheme? Input is the sequence xn, which is a sequence of zeros and ones of length n. Okay, that's the input. What's the output for our scheme? Output is a compressed sequence. So it's a binary code word, and binary code word, let me call it cx. That's the code word for x. This is also a binary sequence, but its length can vary from symbol to symbol. So this is just a finite length binary sequence. So what does the scheme do? In the first step, we count the number of ones in xn. Okay, so we denote it by k. In the next step, we store this count. Okay, so in the next step, what we do is we look at all the sequences with k ones, and we have a list. We have a list of these sequences, and in that list, all the sequences are ordered, and let ix k be the index of the sequence xn among all sequences with k ones. Okay. That's this ix and k. And how do we store the cx? So store cx equals to, this is I'll give a rough description, the binary representation of k comma this ixn k. Okay. So we can depict this in a very simple way. So there are these tables that you form, table 0, table 1, and table k, where table I has all the sequences with 0 ones. I has all the sequences with I1. So this is the one with 0 ones. This is all the sequences with 1 1, and all the sequences with k ones. And you have ordered them in some way and maintained their list. And this ixn, so you look at the table where your sequence exists. That's some table here. Look for this sequence. This is your sequence xn. Its index in this table, the row number is ixn. ixn, sorry, what's the maximum number of ones that you can have? You can have n ones. So this is table n. Okay, and this is the kth table. This is table k. This is where your given sequence lies, and you look at the row number, that's I, X, and K, and store that. Okay, that's the scheme. Very simple. So each sequence here can take different number of bits. Why? Well, because IXN can take different number of bits depending on what K is. Okay. So first question you should ask is, what is the number of bits used to represent a sequence xn in the scheme? So here we note that this number of ones k can take anything between 0 and n. You can have, each sequence can have 0 ones, 1 1, 2 ones, 3 ones, or n ones. Therefore k takes log n plus 1 bits to represent. That's the first part. Okay. How about the second part, I, X, and K? Now I, X, and K can take as many values as the number of sequences of length n will k ones. So I, X, and K can take n choose k values, and so needs log of n choose k bits. Okay. Therefore length lx, length of the code word associated with x, is equal to log n plus 1 plus log n choose k where kx is the number of ones in x. Okay. So one thing we want to understand is, what is this n choose k? So I'll recall a bound here, which we will show later in great generality. That's a quite useful bound. You should remember it. I'll highlight it a bit. So this is an important fact. It's an estimate for n choose k. So n choose k is approximately 2 to the power n, the binary entropy of k by n, where, if you remember, this h, the binary entropy, is simply t log 1 by t plus 1 minus t log 1 by 1 minus t. Okay, we will show this. In fact, what we need is just one side of it. So we'll write a more formal version. N choose k is less than equal to, this is true. When I say approximately, I'm not specifying the lower bound here. In fact, the lower bound is also this divided by something like, I think, square root n into n minus k. So the exponential part remains the same. Okay. So we use this approximation of n choose k. This implies for our scheme, Lx that we use is less than equal to log of n plus 1 plus log of 2 to the power n h k by n. So that's just h of kx by n. Okay, where h is the binary entropy function. Therefore, if you look at the expected value under p, p is the probability with which 1 occurs of this length. This first part is a constant, so nothing can be done about it. Log n plus 1 here, plus expected value under p, let's say under pn, of binary entropy of number of ones that the sequence xn has divided by n. Now, how do we proceed from here? So we do something very nice. We are very simple and nice. We can take this expectation inside because this is the entropy function and therefore it is concave. So this is expected value under Pn. Remember, this number of ones is a random variable. K of xn by n, and this is by Jensen's inequality. Since h is a concave function, so we are using those properties of this function that we have seen earlier. Okay, great. So it's very interesting. This was some function which came out of a counting argument, and that function turned out to be entropy, and that function turned out to be concave. So we can take this expectation inside, and now this thing here. Did I miss something? Oh, sorry, I missed an n here. This is n times this n. So what is this expectation? Let's look at this expectation. Expected value under Pn of k of xn. This is the number of ones in a sequence xn. How many ones do you see here? So one way to see this is the number of ones in the sequence is nothing but summing over all xt. The output will be just the number of ones because xt takes the value just 0 or 1. So this is simply n times, you can take the expectation inside by linearity of expectation. And what is the probability with which xt is 1? Let's call this p. So this is n times hp, and when you n times p, and when you divide by n, this is just p. So this implies that the bound that we have shown is easy to write. This is less than log n plus 1 plus n times entropy of p, our distribution. This, by the way, we are writing it for binary distribution, so this is the same as h of p. Okay. Here, this p is just the probability under p of 1. Okay, so great. So we can take this thing at this side, and what we have established is the kind of bound that we want for redundancy. We have found a bound for how much larger at most is this average length from the ideal average length when you know the distribution. Note that this scheme doesn't know the distribution. This scheme just codes it in a very different way without knowing the distribution. So that's less than equal to log n plus 1. And this is true for every distribution p on this binary alphabet. So for every PMF p on this binary alphabet. And therefore, if you maximize overall distribution, this is also true. So max over p in pxn of the average length of that scheme minus n times hp. This is the average length of the scheme which knows the distribution, which knows the probability with which ones are coming. This is the best that scheme can do. And these two differ by just log n plus 1. Note that this log n plus 1 is negligible in comparison to the best scheme NHP. So this extra cost that you pay for not knowing distribution is kind of negligible here. It's just log n plus 1. So this scheme is great. Its performance, it's great. And it's just logarithmically more than this. There is another, so I'll make few remarks here. Okay, so first remark is what I've already said. This log n plus 1 extra cost for universality because you don't really need to know the distribution p, it's universal for all p, is negligible in comparison with the optimal average length NHP, because that grows linearly with n. So yeah, you are paying a bit extra, but that's not much. It's just logarithmic. Second point, which is also quite interesting, is that remember that recall that probability assignment. Recall that we can find a probability assignment from the scheme. Right? And in fact, what we have shown already is that this Rn star is less than equal to Rn star plus 1, and Rn star is the best you can do, and you can already do log n plus 1 here in the scheme. So this is log n plus 1 plus 1. So this is just log n plus 1. Rn star is at most log n plus 1, and this whatever. Sorry, we have shown a bound for Rn star. We've shown that Rn star is less than log n plus 1, and this is more than Rn star, which means this Rn star must be at most log n. But as we discussed earlier, independent assignments or IID assignments, independent and identical Qn, can only give order n bounds. Okay, some things which grow linearly with n, and the best bound is at most log n. So you can do much better than independent assignment. So indeed, as we mentioned earlier, the distribution that is close to all the independent distributions in the probability assignment problem need not be an independent one. It's a different distribution. We'll say something about it later. It comes, for example, you can just take this length Lx and think of the distribution to the power minus Lxn by the normalization, and that distribution does much better than the independent distributions, any independent distribution. Okay, and the last point is the analysis above can be improved. Okay, this log n that we have can be improved. Just the analysis to get half log n. Okay, so this bound that we had here, the way we did it, this scheme actually we can do a more careful analysis of number of bits used by the scheme, and what you will see from so you can subtract some. So this h is can be smaller than this. This bound is a bit relaxed, and if you use a more careful bound, you will get this to be half log n plus 1. So that's a bound. It's not log n plus 1, it's half log n plus 1. But I think in this case, we don't worry about this constant. In fact, this constant of half is optimal. So yeah, you can't roughly beat this scheme in a universal way. Okay. So we just covered this scheme for the binary alphabet, and it's very simple scheme, very nice. We just count the number of ones and then tell you where is the sequence in all sequences with these many ones. So now we would like to extend this to an arbitrary alphabet. Okay, of larger size. Okay, and for that we need this concept of types. Okay, just for account keeping types. We use types, and I will review some basic things from the so-called method of types, and this textbook, one of the textbook of this for this course, the Chisar-Kernel textbook, that uses this method of types to develop all the coding theorems. But for us, we are only using it in the context of this universal coding. So let me define what is the type of a sequence. So the type of a sequence is simply the empirical frequency vector. So it's, you can think of it, uh, it is a PMF. The type of a sequence is a PMF. Type of a sequence is a PMF denoted by P of X. So type of a sequence, this is about the sequence X, P of X, okay, given by Px of any symbol A is the number of times A occurs in the sequence, NaX by N. Okay, where this guy here is a new symbol I've introduced. It's the number of times A appears in x1 to xn. Okay, that's what this PMF is, and this is defined for all A in X. So that's what type of a sequence is. The empirical frequency vector. Define type of a sequence. And now some more notation. The set of all sequences of a given type, let's say Q, is called the type set or type class Q, type set or type class Q, and we denote it by T Q N. Okay, this, let me use a different T. This is a calligraphic T, T Q N. Okay, and of course the set of all types. So this is the set of all PMFs which are of this form. The set of all types is denoted by, let's say, Tn. Okay, of course it all depends on n, x. So I'm not putting that part here. Okay, note that while type is a PMF, every PMF may not be a type, because yeah, you need this thing to be rationals. But as you take n larger and larger and take union over all types for all n, then you cover all the type. You cover all the PMFs. Okay, but this point is not very important for this course. Okay, so this sequences of a given type, this type set Q has many properties. Okay, the first property of this set, which is the very important property, is that each sequence in this set has the same probability under any IID distribution. So this is one property. Okay, I'll just put it down as a fact. All sequences X in a given type set Q. I'll just omit that N because that remains fixed for us. So I'll not display that. I'll just omit that. All sequences X in Q have the same probability, or have equal probabilities, have equal probabilities under any independent and identically distributed, any IID or product distribution Pn. Okay, so how do we show this? This is a very simple fact. I mean, it's it's easy to verify, but it's a very important fact about this type classes. So let's look at Pn of x for any sequence x of a given type. Pn of x can be written as product t equal to 1 to n p of xt, which can be written as, so this is some interesting thing. What we'll do is, instead of taking this product over all symbols in the sequence, we will take it over all points in the alphabet, and we'll count how many times PA comes. So how many times will PA come here? The number of times PA comes is the number of times A appears in the sequence, and therefore this is of this form. So when I take this up here, I can take that and write it in the exponential form. So it becomes 2 to the power summation over A in x n A x log of PA. Okay, that's interesting. So this is also equal to 2 to the power, I'll put a minus here, NaX log 1 by PA, and I will add and multiply this QA. I'll multiply and divide by this QA. By the way, this guy here is n times QA. That's because the sequence is of type Q. So this becomes 2 to the power minus summation over A in x, this n comes out, QA log QA by PA plus what? All inside the minus. Plus what? Plus the entropy of Q. So this is nothing but 2 to the power minus n divergence between Q and P plus entropy of Q. So very nice. So what it says is that for any sequence x of type Q, the probability under P is just 2 to the power minus n dqp plus hq. It's fixed as long as Q is fixed, as long as the type of the sequence is fixed. Okay, that's very important. So if you look at the set of types and look at the sequences of a given type, what this different sets of types are disjoint, and the union is all sequences. I'll draw this here. So this is all possible sequences in Xn, and we have divided into different types. This is TQ1, TQ2. This is a partition of these sequences into sets with constant probability. In fact, these two probabilities, this is a partition into sets with constant probabilities. Let's just leave it at that. Okay, so that's very interesting. If you look at the distribution under any IID distribution, induced on this set condition on the fact that sequences of a given type, that distribution is uniform. And at a high level, if you want to understand the Chester kernel book a little bit, at a high level, what method of types allows you to do, what that book uses, is it allows you to decompose this this distribution Pn into sort of uniform distribution. And information theory for uniform distribution is very easy. It's just counting arguments, and therefore you can build entire theory around it. This is all at a very high level. But here I've just noticed a very concrete fact. Now, using this concrete fact, we can have a nice result. We can show the following. This is something we'll call the type counting lemma. This will be a bound for the number of types. First we'll note this result, and then we'll show something else using this property. Type counting lemma. So how many types are there for a finite? Of course, we are only looking at finite alphabet. This method is only for finite alphabet. The number of types that you can have. This is a combinatorial question. How many types can you have? And this is no more than n plus 1 to the power cardinality of x minus 1. How do you show this? Well, each type is given by a vector of numbers QAs which sum to 1. So there are x minus 1 degrees of freedom where those numbers can be chosen Further, each of those numbers must have this k by n form, this rational form, and this n a given x can only be 0, 1, 2, 3 up to n. So it has n plus 1 choices. So you get n plus 1 to the power x minus 1. That's the proof. Okay. So therefore, it's very interesting. There are only polynomially many types. Okay, for binary alphabet, there are just n plus 1 types, just linear in n. There are only polynomially many types. Although there are exponentially many sequences in n, but there are only polynomially many types. Uh, that's 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 an important property about the number of types. The other property we want to get about types is something about the cardinality of each type class. So I'll call it type class cardinality lemma. It tells you how many sequences are there of a given type. So it says for every, if you take a type Q, Q is one of these types, the number of sequences of type Q is at most 2 to the power nhq and is at least 2 to the power nhq by a polynomial. This can be improved, but this is a very good approximation. N plus 1 to the power cardinality of x minus 1. So the important point is they are dividing this guy by just a polynomial. So the way to read this result is log of tq by n, the cardinality per n here. The number of bits required to represent these types per symbol is approximately hq. And this bound is rather tight because it will be off by just some log n times cardinality of x minus 1. In this theory, the kind of asymptotics we are looking at, n is very large and the alphabet x is small, fixed. Okay, so you have a lot of words from a given alphabet. If you are interested in the setting where the alphabet itself is very large, the large alphabet setting, that some of there you have to be more careful and do a different kind of asymptotic. And yeah, this large alphabet setting has received a lot of attention in the last 2 decades, especially from the group in UCST. But we will not cover that in this course. So how do we show this? Okay, this coming back to this proof. Okay, these two things are some very important facts about types. So there are only polynomially many types, and the number of sequences of type Q is 2 to the power nhq. Remember that we said that the number of sequences, number of binary sequences with k ones is 2 to the power nhk by n. That's a special case of this result. For the binary sequence, the type is just determined by the number of ones. And therefore, you can use this result to get that approximation that we saw earlier. This one here, which we used in the scheme. So we noticed this fact. This n choose k is less than 2 to the power nhk by n. This is a special case of this more general result applied to the binary alphabet, because for the binary alphabet, type is just determined by the number of ones. And indeed, this bound is also tight there. The number of ones is just n plus 1. Can take up to n plus 1 values. So there are exactly n plus 1 types. So this bound is tight there. And this approximation also applies to that setting. Okay, how do we show this? So the way to show this is the following. This is again a proof from the Chisholm-Kerner book. If you look at the probability of the type set under this PMFQN itself, don't ask me why, it's just a proof that I'm giving you. This probability must be less than 1. Any probability is less than 1. But what is this probability? This is summation over x in this type set of Qn of x. But we saw earlier that the probability of a sequence of given type is 2 to the power minus n, divergence between q and p, plus hq. But this divergence is 0 because p is q here. So it's 2 to the power minus nhq here. So this probability is 2 to the power minus nhq exactly. And this, therefore, this probability is exactly this number here. And this is less than 1, so this implies that the cardinality of the type set is less than, it's a nice proof, is less than 2 to the power n h q. Okay, that's the first part of the proof. The second part of the proof is slightly more involved, just slightly more involved, not too much. And it requires the following observation. You look at the probability under Qn of a type set with type P and look at max of this over all P in the type set. Question is, which distribution maximizes this? The claim is this is maximized by P equal to Q. Okay, that's the claim. We'll show this. So we'll show this. But suppose you show this, then what? Okay, so we'll show this, that the type which maximizes this is this Q. But once you have it, what happens is you can now look at the following. You can now look at the probability under Q of TP and probability under Q of TQ. So this probabilities are the cardinality. Sorry, I'm using this bad notation here. It's not correct. This is not a correct notation. TP, TQ. So since the probabilities under any independent measure for the type set are all constant, so this becomes just the cardinality of TP by cardinality of TQ times the probability under P under Q of any sequence of this type. That probability, as we saw earlier, can be expressed as QA to the power NPA, because the sequence of type P, so it has NPA instances of A. And this guy here can be written as QA to the power N QA. Okay, actually, yeah, this is the proof of this fact that we are showing. Sorry about this. I lost track of my sorry, I lost a track of my thought. Okay, no problem. So we are trying to prove this fact first, and then we later use this fact to derive the other side of the bound. Okay. So this is this ratio. We would like to claim that this ratio is less than or equal to 1. That's our goal here. Okay. So let's look at this guy, TP by TQ times A QA to the power N into PA minus QA. How about this cardinality? This is a combinatorial problem. How many sequences are there with PAAs, PA1As, PA2A2s, PA3A3? How many sequences are there? That's n factorial. This is the multinomial expression NPA factorial and product over all A. Similarly, n factorial product over all A n QA factorial, right? N times A QA to the power N into PA minus QA. So this first product, this is exactly equal to product over A of NQA factorial by N PA factorial of QA to the power N into PA minus QA. So now we'll use an approximation for this guy. It's about K factorial by L factorial is less than equal to, this you can show by making cases, is less than equal to K to the power K minus L. You can show this. So once you have this, so this guy here is, we'll apply this to this ratio here that we have. So this guy here is less than equal to product over A n QA to the power n QA minus nPA. But you already had this PA minus QA. Okay, so this is just 0. And so this is just 1. Okay, and that's the proof of this part of the claim, that this ratio is always less than equal to 1. And therefore, the maximizing one is this TQ. Okay, so what do we do with this fact? Okay, so now what we do is look at this probability 1 over all sequences. So you can take a look at all sequences of a given type P, look at the probability under Qn of all those sequences, and this sums to 1. But what we know is that the maximizing distribution here is Qn of TQ. That's something we just saw. And therefore, this is less than equal to the cardinality of the type set times the probability of this guy. But the cardinality of the type set is no more than n plus 1 to the power cardinality of x minus 1. And this guy, as we saw earlier, is no more than 2 to the is actually exactly equal to 2 to the power minus n HQ times TQ. So when you combine these bounds, you get the cardinality is more than 2 to the power n HQ by up polynomial, which doesn't affect the exponent here. Okay, this is the other side of the bound. So in conclusion, the cardinality of TQ is more than 2 to the power n HQ by this, and it's no more than this. Okay. So we have all the components now to generalize our scheme to a general alphabet here. That's what we will do now. General scheme. So you have given a sequence x in xn. First step you do is find type q of xn. So first you find the type of xn, and then find the index I x q of x in the list. So there is a list with a pre-specified index. That's the table that we have. For each type we have a table of all sequences of type q, and then store the binary representation of the type and this index. Okay, that's the general scheme that extends a previous scheme. We were counting the number of hits. How many bits do you need for representing this type q? Well, you need less than equal to log of n plus 1 to the power x minus 1 bits to represent this because of the type counting lemma. How about the second part? Well, there are at most 2 to the power n HQ sequences of this type, so you need less than these many bits for this part. So this implies that L of x, the length of the sequence that you need, the length of the code word that you associate with a sequence of type q, or let's say for any sequence, is less than equal to log of cardinality of x minus 1 times log of n plus 1 to represent its type, plus n times h of q, where q is the type of the sequence. Therefore, the expected length under Pn is less than equal to plus n times the expected value under Pn of h of p of xn, the type of xn. Okay. So once again we will use the concavity of h to take the expectation inside. So what we get when we do that is this h of the expected type under Pn. That's an interesting quantity. This is a distribution. But what is this distribution? But so just to be complete, this is by Jensen's inequality. Since HP is concave. Okay. So now what is this expected distribution? Well, let's look at it. Let's look at what is the probability P xn of A under Pn. Well, this is the expected number of times you see A in this sequence, and that's n times P of A divided by n, and so that's just PA. So this expected type, this distribution here, is nothing but P itself, the P under which you're computing this. So that's very nice. So this guy here just becomes cardinality of x minus 1 log n plus 1 plus just n times HP, something that we were anyway looking for, so that we can take it on the other side and subtract. So what we have shown is that this scheme, the frequency counting based scheme, it just counts the number of time each word appears and stores it that way using types, is not too much off from the optimal. It's not more than cardinality of x minus 1 log n plus 1 off from the optimal. And yeah, and so one thing we get out of this is that the best scheme that we are looking for is at most this much. Okay, that's for the best scheme, and we have given a particular scheme which is here. One final remark here is that again, this can be improved by a factor of half, but no more. So cardinality of x minus 1 by 2 log n plus 1, this is actually tight. Okay, so this scheme is almost optimal. It's optimal actually for the first order term. Okay, so this concludes our discussion on types and the first scheme. However, the scheme that we presented is not very practical, because you have to enlist all the sequences of a given type, exponentially many of them, and then find where is your current sequence there and store that. That's not efficient. It can only be done for n, for small n. And in the next class, in the next lecture, we will look at a more practical scheme, and we'll finally present arithmetic code and give an idea for the arithmetic code, which is sort of the idea underlying zip. Okay, see you in the next lecture.